Welcome to the 8th class meeting of EECE341, Introduction to Communication Systems. As usual, I want to emphasize that your attendance is very important, even though many of you are absent today. Please regularly check the post-tech electronic attendance system. So if there needs any correction, please let me know. About the quiz 1, some of you may have some complaint. In that case, you direct your regrade request to the TA, and there will be no penalty. We are humans, so we make a lot of mistakes when we grade, so please let us know. Homework 7 is already assigned, as you know, and homework 8 will be assigned. It seems that I'm kind of following the communication and network introduction to communications and networking by giving you homework after every class meeting, and it may help you to keep up with our pace in the class meetings. But let me emphasize that the midterm exam and final exam will be highly mathematical. Right? So quiz problems and homework problems are just to let you keep studying. It does not mean, let me emphasize, it does not mean that the midterm exam and final exam will be like quiz or homework problems. It will be, they will be more like midterms and final exams of signals and systems. Got it? You need a lot of math for the exams. Got it? Okay, my message is simple. Just a second. Okay, my message is simple throughout the entire your undergraduate program. You need to learn how to use these two tools called simplification and visualization. This is very, very important. I will try to show you the examples. Just a second. I will try to show you how to use these two tools throughout this course. Okay, in the last class meeting, I need to do some clarifications first. So last time I talked a lot about the complex envelope and the envelope. And just a second. The starting point was like this. So here goes a real valued bandpass signal. The reason why we talk a lot about real valued bandpass signal is because when we apply electrical signal to our antenna in order to do some radio communications, we model the input to the antenna, transmit antenna, as a real valued bandpass signal. And also at the receive antenna, even though what is impinging on the antenna is a wave, what we get can be well modeled as a real valued bandpass signal. Even though still in these RF cables, inside RF cables, we still have electromagnetic wave propagating through the cable. However, we can well mathematically model the wave as a time function. Anyway, so given a real valued bandpass signal, I just stated that. I didn't prove, but you can get why this is true. But I stated that there exists a complex baseband signal xc of t if you choose your carrier frequency or center frequency. And what happens? Since this is a complex valued signal, if you define the real part as x sub I of t, and if you define the imaginary part as xq of t, then by using the Euler's identity, because this is cosine 2 pi fct plus j sine 2 pi fct. Among 4 cross terms, you have only 2 real parts, which are what? xc of t cosine 2 pi fct minus, sorry, xi of t xq of t sine 2 pi fct. By the way, if you add some theta here, what happens? You can just put thetas here and there. Okay, so if you read some very old textbooks, in order to be precise, they usually add this phase angle theta, and you will see some equality like this. And what I told you can be viewed as a simplified version. Got it? So this may be with theta, the equation with theta may be a more correct one. Got it? So if you read some books, they say that here goes the theorem. Given x of t, real valued bandpass signal, there exists a triplet. A triplet means that a set of 3 things, fc, theta, and xc of t, such that, and they have these thetas. Got it? So this may be more correct one. And also, they introduce some other definitions different from what I derived. I just said that xc of t in the above is called a complex envelope of x of t, or a complex baseband equivalent signal to x of t. And also I say xi of t cosine 2 pi fct plus theta as x of t's real bandpass signals, the in-phase component after we choose fc theta xc, and negative xq of t cosine, sine 2 pi fct plus theta as the quadrature, or some people say quadrature phase component. What is different from our definitions is that there was another one. They have something like xa of t, which turns out to be actually xc of t e to the j 2 pi fct plus theta. And this is called an analytic signal of x of t. The problem is that depending on the author's preference, they sometimes put a coefficient 1/2 or 1/√2. So it confuses a lot, but I'm not going to talk about it. But let me just simply sketch what's going on in the frequency domain. So this is very important. Whenever you study modulation, communication, demodulation, something, think in 2 dimensions, always. First in the time domain, second in the frequency domain. So the idea is like this. Let's consider the Fourier transform of the real valued bandpass signal we are given. So even though capital X of f is complex valued, just for convenience, I have drawn as if it is real valued, but just assume that that is complex valued. Then what can you do is that you remove this part. Just think in that way. And then what happens? You only have that one, right? This is the analytic signal. Ready? So you have inverse Fourier transform of this part only. Then that is called the analytic signal of real value bandpass signal. And then what you can do is you multiply e to the negative j 2 pi fct plus theta. And you define it xc of t. Then what happens? You have xc of f. Ready? So the complex envelope is simply what? The frequency translated version of the analytic signal. Of course, as I told you, depending on the author's preference, different textbooks you put different coefficients. And mostly done is like this. What you do is that you suppose the max, even though it's complex, there is no max. Let's say that the maximum value of this spectrum is A. Then what they do is that they consider 2 times xf. So it's like 2 u of f. Got it? So this height is now 2a. You may say, what? Why we have 2? But it's just for convenience. Okay. Some people use square root of 2. But anyway, so given x of f, you multiply 2 and remove the negative frequency component. Then that is the analytic signal. If you read some books, got it? Some other books just remove. But the majority, I remember, has what? You multiply 2 and remove that part. Got it? So this is the analytic signal, and its Fourier transform is capital X of A of f, this part. And you translate, then you have analytic signal. So what happens? Let's see. Is it really true that we can get our signal back from our complex envelope? So let's do that. So my claim is this. So here, this is the proof, sketch of the proof. Sketch of the proof. What proof? There exists complex envelope, which is a complex baseband signal that equates this one. Got it? So what we are going to do is that we check whether our claim, we multiply 2, we remove negative component, we down translate to the baseband, and that signal, if it is put it here, eventually it becomes x of t. So let's see that. Got it? So this is a claim. X equals real part of xc of t e to the j 2 pi epsilon t plus theta. And what we do is that we work in the frequency domain to prove this. Then what happens? X of f equals anybody? So what we do is that we do not directly do this, but remove this real part operator by doing what? 1/2. What? Real part of some complex number is 1/2 times the complex number plus its conjugate. So we have xc of t e to the j 2 pi fct plus theta plus its complex conjugate. Xc conjugate of t e to the negative j 2 pi fct plus theta. Got it? Now we can Fourier transform the left-hand side and right-hand side. Then what happens? We group these two. So we have xc of t e to the j theta times e to the j 2 pi fct. Then what happens? This Fourier transform translate to the right. So we have e to the j theta xc of f minus fc. And we do the same thing. So here we group this one and that one. xc conjugate of t e to the negative j theta. So if it is transformed, what happens? Capital X sub c conjugate of negative f. So x sub c, sorry. Let's write down that e to the negative j theta first. And xc conjugate of negative f, but we need this, right? Then what happens? Let's see this relation. Then it says that Fourier transform of complex envelope equals what? We have e to the negative j theta, and Fourier transform of the analytic signal translated to the right, right? So we plug in this one, where? Here. And let's see what happens. And suddenly you realize that why I have 2 here, okay? Because it cancels with this 1/2. And then after some manipulations, you can see that this is same as x. Got it? So you fill up these parts. This is a little bit complicated signal gen systems exercise. Got it? So let me tell you again. Your way to prove this one is in the frequency domain. Never forget this, okay? If something does not work well in the time domain, think in a different domain. And one of the domains is the frequency domain. So you have the tool called the Fourier transform, and you can prove it. So let me emphasize the key to prove that. So here, you introduce so-called analytic signal. Got it? That is a kind of intermediate function, which is what? Which is this is interesting, complex bandpass signal or passband signal. Got it? So we define an intermediate, something like catalyst signal called analytic signal that can be obtained by multiplying 2 to the original real bandpass signal and remove the negative frequency component like this. Okay. And then by down translating or moving it to the complex baseband, we get the complex envelope or complex baseband equivalent to the real bandpass signal. And the proof can be done in the frequency domain. Got it? So sometimes, by the way, one of the reason why I said square root of 2, not just the 2 and 1/2, is that we have difficulty when we handle random processes, real valued bandpass random processes. So some authors love square root of 2 when they derive analytic signal. But I really hate that. But many books have that. So if you go to the library or you find some resource on the web, then it may have square root of 2 when they derive analytic signal. And when they do some proof, they may have 1 over square root of 2. But what I prefer is that we multiply 2 and just derive. Okay. And here goes a correction actually. And some of you already solved homework 7. And you found that one of the true-false problem is a little bit different from what I told you in the last lecture. So in the last lecture, I defined the linear modulation as what? As something like this. Okay, where is my pen? So here is so-called a modulator. And here goes the input, which is a message signal. And modulator actually may be viewed as a system that has internal oscillator. By the way, LO means local oscillator. And its convention to put local, it's not global, but anyway, oscillator. And it may have some frequency component, frequency, carrier frequency theta, and FC and phase theta. And then modulator gives us some real valued bandpass signal that can be written as this one. And if we put one more quantifier called linear modulator, then this theta of t becomes constant. And this one must be what? I told you last time incorrectly, A of t is an affine function of the message signal, which means that A of t equals what? Sum A times M of t plus B, which is what I told you last time, but I made a mistake. Actually, an affine function of an LTI filtered version of M of t. So you have some linear time invariant operator here again. Got it? This is the linear modulation. Anyway, so please get the true-false problem correctly. Okay, here goes the overview. We are still working on chapter 3, which is one of the most important chapter throughout this course. When I was an undergraduate student, I took the introductory communication system course in 1994, fall semester, exactly 30 years ago. And my professor spent almost half of the semester to cover chapter 3, and the last half to cover chapter 4. That was all. And the midterm exam was so difficult. So a lot of my classmates dropped the course. But I just persisted. And one lucky thing happened. The final exam was also difficult, and I didn't perform very well, even though the grade is usually relative performance is measured. But anyway, so I was kind of very, nervous at the results. And at that time, there was no privacy something. So usually professors put the exam results and even the final grade on his door, office door. And we were shocked. Everybody got A+. And the reason was that professor was retiring after that semester. And he wanted to give us a present or something. Hey, you took my course up to the end of the semester. Thank you, something like that. And my classmates who dropped the course after the midterm just said, should have not dropped the course, something like that. And what I want to say is that he covered half of the entire semester with chapter 3 and the last half with chapter 4. Got it? I may follow that if I believe we need a lot of explanations. Okay, here goes the review. the most important thing, I thought about this a lot when Professor Yang, who has been usually teaching this course for a long time, asked me to cover him during his sabbatical leave. And I pondered over what is the most important mathematical result throughout this course. And that is what I already have given you. If you have a real valued bandpass signal that has what? Mathematically equivalent complex baseband signal. And from that, you can get what? The in-phase component and quadrature component. So it's like, amazingly, every real valued based bandpass signal can be written in this form after properly choosing FC and theta. Something times cosine and negative something times sine with the same frequency and same phase constant. Amazing, right? And another one was what? By defining xc of t as some real signal a of t, this is real, I kind of revised my first statement. It's not necessarily non-negative, it's real. And we have some phase angle, right? In that case, if we plug in this one there, what happens? We have another representation of a real valued bandpass signal. So these two equations also related with that one, right, is the key equation you need to learn. So this is the most important equation, math formula throughout this course. That's why I emphasize it more than 2 weeks. Got it? I was very shocked when a PhD student, after graduating, he came to my office and saying, "Thank you, professor, I'm leaving." And last word was very weird. He said that, "Professor, I have to confess that I still do not understand why a real valued bandpass signal has these cosine and sine terms." Got it? So it may look very simple, but sometimes, even though those PhDs are repeatedly using this result, some people just never understand. And I hope you do not follow suit, okay? Please understand what's going on, okay? If you have taken my course. Okay, so I've done this complex envelope. By the way, the envelope of a real valued bandpass signal is defined as what? Simply the absolute value of the complex envelope. So very simple. You take the absolute value or modulus. Okay, in the frequency domain, what we need to use is conjugate symmetry of the continuous time Fourier transform of a real valued signal. This is one of the most important results from your signal gen systems. If your x of t is real valued, then its Fourier transform, capital X of f, has what? In the frequency domain, something weird. Let's say that this is the origin, and you take 1 kilohertz. Then what happens? Capital X of 1 kilohertz, that becomes a complex number. Let's say 1 plus j. Then what happens at the negative 1 kilohertz? You always have 1 minus j. That is, these two are conjugate pairs. And if that kind of property holds for all frequency f, the function is called what? Called what? It has conjugate symmetry. Okay? So in mathematically speaking, this is the conjugate symmetry. And when you prove this one or fill up this part, when you fill up this part, you need this one. Got it? you need this property. So play with it, okay? As I told you, in the midterm exam, I may just give you a problem to fill up that ... part where you have to use the conjugate symmetry property of the Fourier transform over real valued signal. Got it? I told you, don't say midterm was too difficult and it was like math Olympiad. No, never said that. Okay, I already told you. If you just cannot understand, and if you, when you ask a tutor, you have tutor for this course, right? Tutor says, I don't know, then you go to the TA. If the TA says, I don't know, come to me, okay? Then I will fill up before the midterm exam. Okay, anyway, so conjugate symmetry is very important to prove this one or to fill up at least this part. And what else? Oh, carrier frequency. By the way, sometimes carrier frequency is called center frequency, but one of the reasons why I do not say center frequency is that according to our theorem, given a real valued bandpass signal whose energy or power concentrated in some passband, you have a freedom to choose carrier frequency. If I say center, probably you want to find minimum frequency component and maximum frequency component and want to find the midpoint, right? 1/2 F min and plus F max. That's not true. That's why I do not want to say center frequency. However, I may use center frequency to mean F sub C from now on, okay? However, you understand that one as a carrier frequency we have chosen, okay? So this is very similar to carrier and center. By the way, whenever we have a real valued bandpass signal, we have our energy or power spread over some carrier frequency, right? If there is no spreading, what does that mean? It's an unmodulated carrier. Or you may say that it's a CW signal, continuous wave signal, without conveying any information. Okay, so let's go back to our linear modulation. And what's the definition now? What is the definition of linear modulation in this course? Linear modulation is what? A linear modulator is a modulator that has what? The output in the form of A of t cosine 2 pi fct plus constant theta. No theta of t, okay? Constant theta. And where A of t, the amplitude, is what? Is an affine function of a linear time invariant filtered version of the message. Got it? So remember in that way, then it would be much easier to understand why we have double sideband modulation as one of linear modulations, why we have single sideband modulation as one of linear modulation, and why we have vestigial sideband modulation as one of linear modulation. Of course, there could be many other linear modulations. There could be many other linear modulations. And the definition of linear modulation, as I told you, is very, very, very vague and has been expanded actually from this original old school terminology, linear modulation. So almost in the end of this chapter 3, I may give you an example of so-called linear modulation that contradicts to this definition. But please understand, because the terminology is not universally defined. Got it? It's like in signal gen systems, most of your professors who taught you signal gen systems just said, okay, if you have a linear system, it has impulse response and its Fourier transform is called frequency response, something like that. But precisely speaking, he or she has to say that if you have a linear time invariant system, right? Because linear time varying system has two variable impulse response. And it does not have direct Fourier transform, even though you can apply Fourier transform to the time parameter, or if you want the delay parameter. Got it? So no definition is universal. So whenever you communicate, even with electrical engineers who took the same course, be careful. Always say that. So you mean this definition. Otherwise, the tower collapses. Got it? Anyway, so last time we've just seen actually this one, double sideband suppressed carrier modulation. And I didn't explain why we call that modulation as double sideband suppressed carrier. It will be clear today after we study so-called pros and cons of this modulation. Pros means 장점 in Korean, and cons means 단점. Okay, so whenever we have some technology, it has limitation or cons, or it has pros compared to the previous technology. And every time engineers wants to what? Remove the cons and emphasize or magnify the pros. And the history is like this. In order to make everything simple, we talk about this one first. However, historically, this was not the first invention, first linear modulation invented. However, we will see the cons of double sideband suppressed carrier modulation. That's why we have double sideband with carrier, or some textbooks says double sideband with large carrier. This means large, okay? And this W is with. It's strange, but anyway. And here comes another important three words that are closely related. Whenever you do some research, you want to do what? Breakthrough research. It's like everybody wanted to improve this system, and no one made a significant improvement. But you want to do that, right? And you want to get the fame, and you want to be recognized. That kind of research has been termed as breakthrough research. So something blocks you, and you break and pass through. In that sense, the breakthrough research or breakthrough result or something was very valued. However, these days, people want something more. They call it now disruptive results. And probably our public servants, 공무원들, wanted to find out a proper Korean Chinese character, and they write this way, 와해적인. Disrupt means that you demolish, you destroy something, right? And destroy what? The conventional wisdom, conventional technique. So it's kind of more a breakthrough. But anyway, then what is this one? Trade-off means that you have three apples and three pears. And what you do is that you remove one apple and you get more pear. And it's all depending on your preference, right? If you love more pears, and you will do that. And if you love more apples, you will do the reverse one. So trade-off research is kind of you sacrifice something you have to get something. And actually, 99% of research and developments are actually focused on this one. And you may say that, well, trade-off research, well, but sometimes trade-off research at the invention of that time, their period, was really disruptive. Got it? So afterwards, we say that, well, that was the trade-off research. Got it? So anyway, what we are going to do in learning this DSB-SC, DSB, WC, SSB, VSB, you will have to focus on what was the problem? What was the cons of the previous technique? And what kind of trade-off the engineers long ago did to kind of de-emphasize the cons and emphasize the pros. Got it? By doing that, you will learn a lot from this kind of history of communication systems. So let's see. And here goes the kind of definition of double sideband suppressed carrier modulation. Of course, a DSB-SC can be visualized well. And if I have a double parenthesis and V means that let's visualize by using some figures, especially block diagrams or Venn diagrams or sometimes equations. So here, double sideband SC modulator, this is DSB-SC modulator, admits a message signal M of t and generates a real bandpass signal X of t, where X of t equals what? Very simple. It's direct, linear. So A of t part is a direct linear mapping. And you have this. Got it? So according to our definition, is this modulator does linear modulation? Yes. Why? Because this A of t part is a linear function of the message. Got it? And what's the, then this is transmitter part, okay? And of course, I have not shown, but we need some amplifier. And at the transmitter, the amplifier is called power amplifier because it increases the power of this real valued bandpass signal a lot. And we have a transmit antenna, TX and TX means transmission, sometimes transmit, sometimes transmitter, depending on your definition. Anyway, then what happens? The antenna emits radio wave. So this is TX. And somewhere we have RX with receive antenna. And some of you have taken my introductory communication and network course, or you are taking my laboratory for communication network. And interesting thing is that, please remember this, usually what we have in the cell phone transmits around 1 watt maximum, okay? Sometimes it goes over that, but 1 watt, 1 joules per second is very huge, okay? So suppose the input to the antenna is 1 watts, okay? And which is equivalent to 30 dBm. By the way, dBm is what? 1 milliwatt is defined as 0 dBm. 30 dBm means 1 watt because 1,000 milliwatt, okay? So you need to be get acquainted with this number, 30 dBm. But sometimes 0 dBm transmission is not rare. Okay? You may say that, oh, 0? No transmission. No. 0 dBm means 1 milliwatt. Okay? Be careful. 0 dBm is 1 milliwatt. And your Bluetooth is around that range, just simply put. And what happens? Suppose you have 2 antennas, transmit antenna, receive antenna. You apply 0 dBm power to the antenna, transmit antenna. And here at the receive antenna, what happens? Only a very small fraction of the transmitted power or energy is what? Is moving the electrons in the antenna, because our antenna is usually made of conductors, right? And you have to find out what message signal is there in the signal. with that very weak signal. Usually what happens is that at the end of this one, suppose you are measuring the Wi-Fi signal. You know what is Wi-Fi. Wi-Fi signal at the output of your receive antenna. Usually the received power is what? 0 to negative 100 dBm range. Okay? Even if you can see the access point, you may see from your cell phone, especially Android phones, they have direct access to the received signal power. Sometimes it's negative 40 dBm. What does that mean, negative 40 dBm? How many watts? 10 to the negative 4 milliwatt. Got it? Very small, very weak. And can you drive any electronic circuit with this small power? It's very hard. So what they do is that they put an amplifier. And this amplifier is called something amplifier, and usually it is called LNA. And LNA is the abbreviation of low noise amplifier. And there is a reason. Okay, sometimes you can just use power amplifier, even though it's labeled as power amplifier. You can use it as a amplifier in the receiver, but usually we call this amplifier as low noise amplifier because we want to put an amplifier that has very small noise figure. And I'm not going to emphasize too much about this term noise figure, but if you major in RF electronic circuits and antennas, this term noise figure becomes very, very important. Okay? But I'm not talk too much about this one. But anyway, so interestingly, you have an amplifier needed in the transmitter. Because anyway, you want to transmit your power as strong as possible as far as you keep the regulation. Usually governments have regulation on the transmission power of your equipment. You cannot transmit, for example, 1 megawatt using your cell phone. Physically impossible, but if you do that, probably my brain will be fried immediately, right? So we have health concerns about the large power radio wave. So many researchers in the world did a lot of study, and they provided data to the governments and UN organizations such as International Telecommunication Union, ITU, and they share the information and have each nation's regulation. And for example, in the ISM band, one of the bands of Wi-Fi, 2.4 gigahertz band, there is a regulation. You cannot transmit your radio signal with input power to the transmit antenna more than some milliwatts, something like that. Got it? Anyway, but we need anyway power amplifier, and we need low noise amplifier. And then what do we need to do? We amplify the signal and want to extract the message signal M of t, right? So for simplicity, let's just say that at this point, the signal is called Y of t, because now we can again model the signal, even though it's precisely speaking, it's a wave through the RF cable, but we can just model it as a time function. And we may have some B M of delay cosine 2 pi fc t minus delay plus theta, something like that. Assuming the channel between transmit and receive antenna only gives you attenuation of the signal power and the delay, propagation delay. Of course, the actual channel between the transmit and receive antenna is much more complicated. So this is simplified model of the receive signal. And we do again, let's say, okay, let's forget about this delay. Okay? Let's say just m of t cosine 2 pi fct plus theta. Then what do we need to do to extract m of t? And one of the way is this one. You multiply here. The same carrier part. So cosine 2 pi fc t minus tau plus theta if you want to keep the tau. And if you do not want, just remove that. And what happens at the output? Just a simple high school trigonometric. So you have b m of t cosine 2 pi fc t, if you want tau, squared. And what? You've usually proved the trigonometric identities in the context of geometry. You draw a lot of circles, triangles, right? To prove the trigonometric identities. But we don't do that. We just draw the graph. So suppose you have cosine 2 pi fct. Then you have something like, you have something like this, right? Now, what happens if you square it? Let's forget about the phase, okay? Then this 1 becomes 1, and negative 1 becomes 1, right? And 0 becomes 0. So when I first saw, I still remember, I'm kind of remembering something not important, but when I first saw the trigonometric identities about cosine square theta, I draw a figure as a function of theta, but in this case, function of t now. And I thought it would look like something like this. Right? Something like jump down, jump up, something like that. And it turns out to be, amazingly, very smooth curve. Right? And even the result said what? This equals 1/2, 1 plus cosine 2 pi 2 fc t. And now, since you know the graph, what is this one? It's after removing this 1/2, the mean value, right? What? You have another cosine function. But its frequency is doubled, right? And the variation is reduced into half. So this is what you have, right? So now this is your kind of self-homework. I'm not grading, okay? So if you do the high school tutoring, try to prove, one was that prove the trigonometric identities using Euler's formula. And second one is that draw graphs every time you want to show the result. Got it? Anyway, so this part can be written as 1/2, 1 plus cosine 2 pi fc. This is complicated. Let me just double the entire thing. Okay. Anyway, 4 pi fc t minus tau plus 2 theta. Okay. And if you expand, you have what? You have the first term, and you have the second term, right? Now, what do you want to do? Assuming 2 times, this is 2 times 2 fc. 2 times fc is much larger than the bandwidth of the message signal, then what happens? what do you need? You just need to put a low pass filter that removes that one to get the scaled version of your message signal, right? So whenever you are given a double sideband suppressed carrier receive signal, what you need to do is what? You need to find out the exact carrier frequency and the phase angle of the received signal, right? And you regenerate cosine function using some local oscillator again in your receiver, and you multiply your received signal with your local oscillator signal, and what? And perform low pass filtering. By the way, what kind of mathematical operations is done here? First, what is this one? Mathematically speaking, that one does what? That one multiplies a constant, right, to the input signal. Can you multiply a constant to an electrical current or voltage signal? Yes, you can. Use amplifier, right? Right? So this can be done by using amplifier. And of course, that component is called low noise amplifier here. And second one is what? This one is a little bit more complicated. Let me just use X as an input, Y as an output for convenience. Consider a system that can multiply some real valued bandpass signal with a local oscillator signal, CW signal. Can we do this? You have amplifier, right? To do this operation. What about that one? And circuit guys have invented amazing passive component called mixer. It's a 3-terminal passive device, an RF mixer. And what you do is that you apply this local oscillator signal. You apply X of t, and you get amazingly the product of these two inputs as the output. Isn't it amazing? Electrical engineers, especially circuit guys, old school circuit guys, did what? Did make it possible to perform mathematical operations like addition, subtraction, multiplication, division by using innate, right, lifeless material. Isn't it amazing? When I first realized that one, when I was even after did my military service. It's like after 2 years, I did military service for 1.5 years because I was a so-called 방위병 at that time. And then came back, and one day I suddenly realized that it's amazing. We are letting metals, wires, plastics, some silicons to do mathematical operations. Isn't it amazing? We let silicons to memorize some data. We make the magnetic domains to memorize our email, something like that. Really amazing, right? Anyway, so RF mixer does what? Multiplication. And here comes the difficulty. Suppose you have a friend who is a musician. and they use a lot of electronic equipments. And you visited his or her studio. And your friend says that, hey, here goes a mixer, and there is something. And you say that you want to say, you want to show that you are knowledgeable. Hey, I know what is a mixer. Be careful. They use the term mixer totally different way. Their mixer means, in our term, adder. Okay? What they do is that they record the voice of the singer totally separately with the background music. So what usually they do is that they call, for example, orchestra and record the song without the song. And if it is perfect, and then they call the expensive singers to come to the studio. And that's why they usually put a headset. That is already what? That plays the recorded version of the song without song. And then here is a non-echo chamber and a very sensitive microphone, and the singer songs just listening to that one. That's why you have some booths in the musician studio, and they usually put headset and sings the song. Got it? And what mixer does what? They have a recorded version of the singer's voice without any background music, and there is a music without singer's voice. And what they do, they sometimes change the amplitude or power of these two. Because consider that you have an orchestra, you have a very expensive singer, and you record it and find that the lyrics of the singer cannot be audible because of the strength of the background music is too large. Then are you going to ask the expensive singer to come again? And, oh, okay, please, we made a mistake in recording. You can't do that, right? So they record separately, and they do a lot of tuning. And sometimes they changes the frequency of the singer's voice because the singer made a mistake in reading the note. Anyway, that is called mixer. So be careful. Okay? Mixer for musicians. Okay. Is in our term an adder. Okay. Be careful. RF mixer is what? A multiplier, mathematically speaking. So we want to do multiplication. And the last part is what? This one. Hey, we know what is low-pass filter. You learned in circuits and systems course, and you learned it in signal-gen systems. Amazingly, by using resistors, inductors, and if you want capacitors or vice versa, then you can do what? You can perform some operation that can be only understood in the frequency domain. High frequency components are all shut off. Low frequency components only pass through that lifeless box. Isn't it amazing? So the idea of double sideband suppressed carrier modulation and demodulation is very, very simple. It can be understood even by a high schooler as far as he or she understands LTI filtering, low pass filter. It's not possible. So, but that cosine square part, right? That can be understood because cosine square theta equals 1/2 1 plus cosine 2 theta. Of course, in our case, we always view sine and cosine function as function of time because we are electrical engineers. Anyway, now, what is the problem? As I told you, you have to find out what is the cons and what are the cons and what are the pros of this modulation. So think about that. Suppose you are kidnapped by an alien. Okay, you are deserted in a planet, not the alien's planet, but some very remote planet, and you found that, hey, there are kidnapped Egyptians kidnapped 10,000 years ago, and they still live their life. Got it? So they build pyramid, and suddenly you were placed in that area, and you are very knowledgeable, right? You know everything, every math. You have 2,000 years or 10,000 years knowledge in math. And even you are educated as an electrical engineer. And you now become a king or emperor or Ra or Pharaoh of the new culture. And what are you going to do? Probably you want to build a radio to say, help me, I'm kidnapped, help me, right? The problem is what? You know the double sideband suppressed carrier modulation. So you order those your servants. Hey, build DSB-SC modulator. I want to communicate with Earthans or Terrans in the Earth. They may rescue me if they hear. And they may say that, what kind of thing do we need to build? You may say that, okay, first, what about microphone? I may say some message and I want to convert it to an electrical signal. They say, what? Micro what? So that's the problem, right? Suppose you teach them, okay, this is simple electromagnetics and you have a magnet and there is a membrane vibrating and you have electrical induction that gives a change of current, blah, blah, blah. So they built it. Okay. And what do? You may say that, hey, amplify my voice. How? Transistor? You can't find any transistor. Probably what you want to do is what? Let them build a vacuum tube, right? Vacuum tube was a kind of prototype of transistor now we use, right? Okay, so they invented light bulb and you let them invent light bulb called Egyptian named Thomas Edison, invent a light bulb and change that to a vacuum tube. So you now have an amplifier. Then what you do? You may say that, okay, let's build 1 kilometer size transmit antenna, and in order to have a power efficiency, let's generate local oscillator frequency around megahertz. And they said, what is megahertz? And you may say that 1 million oscillations per second. And they say, what? Anyway, you let them invent 1 megahertz oscillator. And what will happen? So you have local oscillator signal and you have your voice signal amplified. You need multiplier, right? Mathematically, you need multiplier. So you ask some group of slaves called electrical engineers and ask them to develop RF mixer and power amplifier and antenna, and you transmit. So now you have to understand this one. There are 2 types of electrical engineers, even in this building. Okay, I'm on the right side of the building, the right building, and some people on the left building. In the right building, people devise mathematical, logical, some operations that makes something good, right? For example, in double sideband suppressed carrier modulation, if you can generate local oscillator signal, continuous wave signal, if you can multiply the signal with your voice signal, which is already converted from acoustic to electrical, and if you can amplify the signal, then what happens? You can let the radio wave convey your voice. And in the receiver part, what is good? If you can amplify the received signal, that would be very, very weak, right? And then if you can generate local oscillator signal that has the same frequency and phase with the received signal, and again, if you can build a multiplier, and again, if you can build a low-pass filter, then what happens? Of course, you need a speaker, but anyway, you can do voice communication. So these people on the right building, think about mathematical, logical operations that is good for human being, right? Hey, we want to do some wireless voice communication using radio, 1,000 kilometers. Here are mathematical procedure. And the other building, left building, there are sometimes not only electrical engineers, but also physicists, chemical engineers, chemical engineers, and sometimes material science engineers, sometimes chemistry scientists. Those people study what? They want to build some electrical components and sometimes circuits that does this mathematical operation. And what happens if these two buildings, engineers or scientists work together and their results is successful? We have our new product. That's the way how the electrical engineering has changed this world. Got it? So in this course, most focus is on this right side, theory, math, and what is good if this is done. Okay, and if you take, for example, RF electronics circuit course, some circuits course, semiconductor related, you take courses related to this left building. Got it? And I hope as a third grade or fourth grade student, still you have to take a lot of courses in both buildings. Do not too early focus on one of the buildings and study only that one. That limits your capability a lot. That's not good. Anyway, so let me stop here. And what is important is that next time I'm going to talk about what is the problem of this DSB-SC demodulator and why people have developed double sideband with carrier or large carrier system. Okay, that's all for today.